Welcome to Ask and Learn.
We are given a generic reversible reaction to model how adding heat to the double helix structure of DNA causes the hydrogen bonds that form that structure to break and therefore cause the two strands to form two different random coils. In part A, we want to determine whether the sign of the change in entropy for the forward direction of this reaction is positive or negative, and we want to explain how we know. So remember that the total entropy of a given system can be correlated to the amount of disorder or randomness in that system, so that an increase in randomness or disorder is equal to an increase in entropy. If we examine the reaction that we are given, we see that the word random even appears on the product side. And when we go from the left side to the right side in the forward direction, we start with one molecule of DNA, a double helix, two strands bonded together to two separate strands. So we increase the number of molecules and therefore increase molecular complexity and randomness. And that means that to go in the forward direction for this reaction, we increase entropy. And that's why the change is going to be positive. Because since we increase entropy, we have a higher value for the entropy on the products than on the reactants. And the change in entropy is the entropy of the products minus the entropy of the reactants. And if we have a higher value for the entropy of the products than the reactants, then when we subtract them, delta S comes out to be positive. And so that's the explanation as to how we know that the change in entropy, delta S, for this generic reaction will be positive. In part B, we want to know, based on the equation delta G equals delta H minus T delta S, we are told that this product of the temperature and the change in entropy is smaller than the value for delta H. And so because of that, we say we can plug in some numbers in order to qualitatively see whether delta G will be positive or negative. And we know that delta H is greater than T delta S. We are subtracting T delta S from delta H. So if delta H were to equal 2 and T delta S were to equal 1, when we subtract them, we get a positive value of 1. So since we know that delta H is greater than T delta S, for any values that we plug in for those, the result, meaning delta G, will always be positive, meaning that reaction will always be non-spontaneous under those conditions. So that comes out to a positive value for delta G, meaning it's greater than 0. And finally, for part C, we want to derive an expression for the temperature T in terms of delta H and delta S when this reaction is at equilibrium. Remember that when a system is in equilibrium, that delta G equals 0. And when that's the case, we can get rid of this term, delta G, and set it equal to 0, and move over the product of T delta S to the other side, so that we can write out this equation now as delta H equals T delta S. And now we just need to isolate T by dividing over delta S. And our final equation for T at equilibrium is delta H divided by delta S.